logistic growth model with an application, and then continue with the first two modules that I did not say anything about. Okay. So we are in section 4.5. We're trying to finish chapter 4 today and move on. So I'm looking for another problem with logistic growth model, and then we look at the exponential growth and exponential decay. Okay, so let's look at problems 38 through 42. And this is on page 531. And we are given a model. I'm going to copy the model and then we'll read the problem. 12.57, everything divided by 1 plus 4.11. If you can't see, stop me anytime, okay? E to negative 0.026. X, of course. Okay, so now let's read the problem. The logistic growth model for the world population, so this is in billions. And it's people. Okay. X years after 1949. X equals what for 1949? X years, the number of years after 1949. So what do we conclude 1949 represents?
Going to be 0?
Yes, of course. That's the initial value, initial time frame. Yes. How well does the function model the data shown in the world population for 2000? So we're asked to find in number 38 what happened in the year 2000. Then in number 39, and then we'll compare to a table. How well does the population, how does the function model the population for 2010? When will the world population reach 7 billion? When will the world population reach 8 billion? That's okay, it's the same thing. And then number 42, the limiting size of the population. Okay. So what are we asked to do first? In number 38, in problem 38, they're asking us to determine the population according to the model. We know what the population was. They're telling us that in the year 2000, the population was 6.1 billion. This is given. What we would like to determine is how far from 6.1 billion will the answer be for the model. In other words, is the model okay for the year 2000? It may be okay for 2000, it may not be okay for 2010. It may be okay for 2015 and not for 2020. But we're asked specifically for 2000. So what should I do to determine the population from the model for the year 2000?
Put 51 in for X.
Very good. If X equals 0 is for 1949, for 2000 is X is 51. Of course, here I'm going to add 10, so X will be 61. So in the graphing calculator, I want to put this function in y equals. It's the best thing to do, the easiest thing to plug in everything and then put in 51 and 61. Okay, so don't forget, since this is just one term, it's okay not to put parentheses around it. But here in the graphing calculator, we have to put parentheses. So let's type in 12.57. Stop me if you have questions, please. In parentheses, 1 plus 4.11. Remember where E is with the same key with natural log. So E raised to please put it in parentheses, the power, negative 0.026x, close the parenthesis for the power, and come down and close the other parenthesis for the denominator. Bring the cursor down and then close. And now all you have to do is just go to second and table after you do this and plug in 51, enter, and 61, enter. So f of 51, I got 6.010 billion. And f of 61, I got 6.826 billion people. They're asking us to compare the 6.1, the actual, to what we found with the graphing calculator. So 6.1 and 6.0, they're not that far apart. I wouldn't say the model is, yeah, it's not the same. We're talking about 90 million people, but now for 39, they are telling us that for 61, they say the actual is 6.9. So this is much better. For 2010, the model is much better than for 2000 and for 2000. Not as good. But it works for 61. It doesn't have to work for all of them, but for 61, in other words, for 2010, it's a much better approximation of the actual. This is the actual, and this is what the model gives us. Here the actual is 6.1, and this is 6.0. So not as good. They're asking us, when will the population be 7 billion? So what are we asked to do now? In problem 40. So this was 38, this is 38, this is 39, and now 40. They're asking us, when will the population reach 7 billion? So what are we going to do for that?
Find x.
Exactly. So this time we are given y, which is the function f of x. This time we are given 7 billions here. And this is 12.57 divided by 1 plus 4.11 e to negative 0.026x. This is not a trivial equation to solve. We will make it very easy, but when you look at it, you'll say, uh-oh. So it's not, if you don't notice something here, or don't think of cross-multiplying, for example, we will definitely make it more difficult. So I'm going to cross-multiply, because this is a proportion. And only in a proportion we are allowed to cross-multiply. So, okay, I got a couple of very tired pages. I'm just going to recycle those. Okay. So 7 times all this, do not multiply, leave it alone. Just write it like this. Well, of course, close the parenthesis, equals this times 12.57. Can anyone suggest a next step? The obvious next step.
Divide by 7.
Very good. 1 plus 4.11 e to negative 0.026x equals 1257 divided by 7. Don't worry about it. Leave it alone. What is the next obvious step?
You have to bring the exponent down, or minus the 1 first?
Yes. Yes. I have to completely clean it up. I am trying to solve for this first, and then yes. That would be the next step. So first I have to move 1. So 4.11 e to negative 0.026x equals 12.57 over 7 minus 1. I still have one more step before I bring the exponent down. And that is this.
Read the decimal?
Yes, we have to divide both sides by this number. So e to negative 0.026x equals 12.57 over 7 minus 1. Now you can say, what about this? Leave it alone. Don't even look at it. It can wait patiently. We don't have to do anything to it. We will obviously apply natural log to both sides. We have no choice. When we apply natural log to this side, we'll bring down the negative 0.026x. I should have written in here natural log e, but what do we know? Just a side note. What do we know about natural log e?
They're inverses? So it's 1?
Exactly. It is 1. That's why I didn't write it. So now I'm here with natural log of all this catastrophe. Don't worry about it. Don't even look at it. Just copy it identical, in identical mode. All I have to do now is divide by this, and this is x. The reason why we don't want to approximate this is because we introduce error in the calculation. So do not approximate it. We will perform all calculations in one step. So I have to divide by negative 0.026, and I copy that whole thing. Natural log 12.57 over 7 minus 1, and everything over 4.11. Okay. Natural log. Careful how we enter this. So these are the parentheses that already pop up in natural log. But now we have to have parentheses around this. We don't have to put parentheses around 4.11. So left parenthesis again, 12.57 divided by 7, and then minus 1. Close the parenthesis for the numerator, and now divide by 4.11 and close the final parenthesis, which is this. And then further divide. Don't forget to put parentheses now because it's a negative symbol here. Negative 0.026, close the parenthesis and press enter. We can always double check. There is no issue here. You'll see in a moment. So x appears to be, according to my calculations, 63.15 years. What does that mean? Well, you add 1949 to it, and that appears to be in 2012. And we know that that's pretty close to the truth because we already know that we exceeded 7 billion in the world. We can always go back and check. How do I go back and check? If I don't trust my number, I can always go back here, plug in 63.15 in here, perform all the calculations, and I should get very, very, very close to 7. If I use the entire number, I will definitely get 7. So leave it alone. I performed another calculation already. So yeah, I will not get exactly 7 billion. Okay, so 1 plus 4.11, and then E, and in parentheses, negative 0.026 times 63.15, close the parenthesis for the denominator, and when I hit enter, I should get very, very close to 7. I will not get exactly 7, but I know that. I got 6.9999988. Pretty good. So I know that according to the model, in the year 2012, population was 7 billion. Now, they're asking us the final question here that I would like to work on, the limiting size of the population. What does this mean? As time goes by, approaching, if you want, infinity, I know that's not possible, but limiting size. So in the function that I already have in the graphing calculator, I will plug in, let's say what happens if I plug in 63.19. It was 63.15, sorry. 63.15. I better get 7. Yes. Let's say 100 years from 1949. Let's say 1,000 years. Let's say 2,000 years. What do you see happens? Let's say 3,000 years. What happens? What number do we get? Let me know what you got. So that
The 12.57?
exactly, because that's the horizontal asymptote. So if the model is true, and we get to 12 billion, we are not, according to the model, we are not going to be able to live on the planet anymore. We'll have to find another place to extend. So, so in problem 42, as t, it's not t, it's x, I'm sorry. It's the same thing. As time approaches infinity, f of x approaches 12.57 billion. I hope that's not the case. I hope the model doesn't hold. So then we can get capped at 12.57 billion. But it will not happen anytime soon. Okay, so now we have two more models. Exponential growth. And this is the amount at time t equals the initial, the starting point, times e to kt. This is the initial. This is at time t, its amount, and t. Amount at time t. E is our friendly number. K is the exponential, the growth rate, annual growth rate. And this is time in years. Okay, so let's look at the problem with exponential growth. We had this before because this is very similar to the continuous compound interest. It's the same formula. Okay. 26 caught my eye on page 539. We're given a function a of t equals 82.3 times e to for some I started and I have to finish it now. So this one has negative in here, so it will be an exponential decay. My apologies. I just picked it. I want to continue it now. It's the same thing. So let me refresh your memory on the exponential decay. When it comes to population, we can use the same notation. It's normally for a mass, but it doesn't matter. The notation is not important. So it's a of t equals a0 e to negative kt. Everything is the same. The initial, e is the same, k is the same, t is the same, a is the same. The only difference between exponential decay and exponential growth is the sign in front of k. Since this one, I picked it and I didn't want to go back and erase this. So since this one has a negative in front of it, it's an exponential decay. We're going to find another one with plus in front. We're going to practice that. Same thing. Okay, so let's see what they say about this model and what does it give. It models the population of Germany, A, in millions, T years since 2010. So this is in millions. People, of course. I don't need, okay. T is time in years, of course. And it says since 2010, which this represents then, since it's initial, 2010 means 0 years, as we just had in a different example. Okay. What was the population of Germany in 2010? So I'm just going to copy so I can put this book away. So part A, the population in 2010. Part B, is the population of Germany increasing or decreasing? Increasing or decreasing. And part C, in which year will the population of Germany be 79.1 million? 79.1 million. So these are our 3 questions that we need to look at. So the first one is very clear what we need to do in order to find what happened in 2010. In 2010 is the initial population, so all we have to do is just replace t by 0. So when t is 0, f of 0, very simple, it must be the initial, because 0 times a negative number is still 0, e to 0 will be 1, so this is the number, this is the starting point, 82.3 million. Now, if the population is increasing or decreasing, we already know that, but here's what I recommend. So we looked at 2010, and we realized that at that point, the population is 82.3 million. If we're not sure, let's say what happens in 2020, which is this year. Let's say 10 years later. So let's plug it in and determine. So I have 82.3 times E in parentheses, negative 0.004 multiplied by 10 and close the parenthesis and press enter. And I got 79.07. So this is 79.07 million. So then what is our conclusion? Is the population of Germany decreasing or increasing? Of course, this book, I think, was published before the influx of the migrants. But according to the model, obviously, in 2010, this was the amount, the number of people. In 2020, this was the amount. So what do we conclude? Is the population of Germany increasing or decreasing?
Decreasing.
Yes, very good. So this was part A, and this is part B. I just determined arbitrarily the 2010 and 20 because I already had that, so I just picked another year, and obviously it's decreasing, so F is decreasing. And part C, we are asked to find what happens, when will the population, and you can say you already found it, true, but this was just for our calculation in part B. Let's assume we don't know that. How do I determine when will the population be 79?